Welcome back to another video, guys. In this video, I have for you guys 5 different push button power latching circuits for the Arduino or whatever microcontroller that you're using. Now, if you stumbled across this video and you're not familiar with what a push button power latching circuit is, or a soft latching power circuit, then just think of any modern device that you've used with a very small momentary push button to push to turn the device on and push and hold to turn the device off. So what we're gonna do here is we're gonna recreate those circuits on our breadboard, and we're gonna do it in 5 different ways to tackle the same problem. And additionally, the push button has a second function. So when the device is on, we're gonna use that push button and we're gonna use it as an input for our microcontroller. So now I can't claim that I came up with all 5 of these circuits myself. There's some great, smart, and generous people on the EEV blogs forum. So I'm gonna put a link in the description to the discussion that I created where people actually came up with some of these circuits themselves. And then of course, I'm gonna show you how I breadboarded them, what components I'm using, and I'll explain how the circuits work so that you guys can integrate them into your own projects.
All right, so this is our first circuit here, and this is actually a circuit that was taken from another YouTube video, but there is one small problem with it, which someone on the EEV forums helped me resolve. So I figured I'd repost it here in my video with the correct schematic. So we'll get to that correction in a second. But as it stands right now, we have on the left-hand side our voltage source, positive and negative. It could be a battery or another voltage supply. And up here we have a PChannel MOSFET. And so on the source side of the PChannel MOSFET, we have our voltage source positive. On the drain side, you'll see that it runs down in here to our voltage regulator on our microcontroller. So on our Arduino, this would run to the VIN pin. Now, on this side here, we have a 1 mega ohm resistor, basically pulling the gate high on the PChannel MOSFET. So I'm going to clear that up so we can see this better. And so it's pulling this gate high. And so this is actually right now going to be keeping this whole thing off. And so no power, no current is going to flow into our microcontroller, and everything should be off right now. Now, as we press the push button, which you see here, what that's going to do is that's going to allow us to basically just short this out. And you're going to see the path of the current coming down here to ground, and that's going to turn our PChannel MOSFET on. So now this thing's going to be on, current's going to start flowing to our voltage regulator, and in the first line of code that we have on whatever pin that we've designated as our hold power pin, this out pin here, it should be pulled high. And so it's going to pull a high signal here to the gate or either base of this transistor here, this BC414N type transistor. And what that's going to do is now that's going to allow the current basically to flow in this direction here, and it's going to actually keep this gate low on our PChannel MOSFET, keeping this whole device on. But the key here is, like I said, in the first few lines of code, putting a high signal on our out pin over here. And that's going to latch the power on until we actually pull this pin low. And then once it's pulled low, that's going to turn this transistor off, which again is going to be able to pull this gate high and then kill the power to our microprocessor, turning everything off. Also, as I mentioned in the introduction in this video, when you press this button momentarily, that is actually going to trigger an input on whatever input pin we've connected this to on our microcontroller. Now to do that, this actually on our Arduino anyways, we have internal pull up resistors, so we're going to pull those high. And when that's pulled high and this button is pressed, we're going to have an active low signal that's going to come in here to ground when the button is momentarily pressed. And I should also mention that when I mentioned earlier that pressing this button is going to turn the circuit back off, it's actually turning it off through software. And so when you actually push and hold this button, you're going to have something in your software on the input here to monitor the input and figure out how long you've pressed that button. And for example, if you press it for, let's say, 3 seconds, then that's going to pull this pin here low, and that's again going to turn this whole circuit off. So it's not done through the hardware, but it's actually done through the software. So this is the whole idea behind a soft latching switch. And so that's kind of how this works. And so the problem I was having with this circuit was with this capacitor right here. And so what was happening was the very first time I connected my power leads to this circuit, the device would default to turning on, which actually it shouldn't. We want this thing to remain off until we input this switch. And so I think what was happening here, what was described to me actually, what was happening on the EEV blogs forum, was that this capacitor was taking too long to charge up through this 1 mega ohm resistor. So the very first time this device was actually powered, given any sort of power, this cap was taking too long to charge and this gate wasn't being pulled high. So therefore the device would turn on and it would have enough time to boot up and, like I said, default to on. Now if I disconnected the leads here and then I reconnected them rather quickly, this capacitor didn't discharge and then the circuit would behave as expected. And so what was done to resolve this issue was actually take this capacitor from this position and just move it in parallel with this 1 mega ohm resistor, and everything seems to work flawlessly. And we'll see that on the actual circuit board in a second. So now moving on to the breadboard, we have a single Arduino micro here that's going to be plugged into each of the 5 circuits to demonstrate the functionality of the power latching circuit as well as the input detection. So when this thing is turned on, you should see the faint blue glow from the Arduino micro's built-in LED showing that it's in the on state. And when we detect an input, the built-in green LED should light up for a short button press. And if we have a longer button press, it's going to light up very shortly, once per second, for however long we're holding the momentary push button. And anything greater than 3 seconds, it should turn itself off. So we're going to, like I said, cycle through each of these circuits. The first one being the circuit that we just went over. And so when I have my power supply set to 12 volts, I'm going to connect the ground up here, and you'll see that this thing remains off. Now if I very carefully press this small switch, you see the faint blue glow of the LEDs, which is great. So far so good. Now if I do a very short button press, there you go, the green LED lit up. If I do a longer button press, once per second, that green LED is lighting up. And if I do a button press more than 3 seconds, 1, 2, 3, it should shut itself off. There you go, the blue light's off and the Arduino has shut itself off. So this first circuit is working as expected, and we are going to move on to the next schematic. And so this next schematic here was found on the internet. Somebody also supplied it on the EEV blogs forum, so they found it on the net too. But basically it has a similar principle in operation to the previous schematic. We have a P-channel MOSFET up here, an N-channel down here. It comes in this dual MOSFET package. And what it's doing is, as soon as power is applied to the input, as long as the jumper is in the auto off position, the gate on the P channel is pulled high and no power is being supplied to the microcontroller. So everything is off at this point. Now, as soon as the push button down here is pressed, what that's going to do, it's going to give this a path to basically pull low. And so the gate here is going to get pulled low. We're going to get current flowing to our microcontroller and it should turn on. Now, where the schematic is a little bit different is that it does have this resistor capacitor combination over here, which should latch the N-channel MOSFET gate high. And now that's going to continue to provide a path to ground once the momentary push button is released, and that's going to keep the whole circuit on. So it's actually being latched through this section here rather than through an output pin on the microcontroller. Now in practice, I could not get this to work on my actual breadboard. I'm not sure what was going on. If you guys have any suggestions, please let me know in the comments down below. But again, you'll see that in the next clip where I actually show the breadboard operation. The microcontroller turns on momentarily, but as soon as the push button here is released, everything turns back off. So there's no latching action that I could get working in this section of the schematic here. But the idea here is this press on, controlled shutdown, and hold off. So the advantage here is that this is still has an input pin, and so if you hold the button down, the idea is that the capacitor here should discharge through this route here, and then after a number of seconds, it should actually pull this gate back low and the whole thing will shut off. And during those last few seconds, the input pin here sees that the button is being held low, and it allows the microcontroller to clean things up right before it gets forced to shut down. And so again, that's the advantage. You get a clean shutdown with any last processes for the microcontroller being processed before being forced off. And it also, the forced off also allows you again to force this device off in case your microcontroller freezes, and so that if it's stuck in some sort of loop and you can't provide an output low to ground, it actually discharges and forces the whole thing off, and then you can reboot. And like I said, in the next clip here, you'll see that I can't get this to work.
And so moving on to the next circuit here, this is the only one of the 5 that I cannot seem to get working properly, but we're going to try it out anyways, and I'll show you what it's doing. So I have my positive lead connected, and now my negative lead is connected, and so I got 12 volts powering this circuit. When I go to press this momentary push button, you'll see the faint blue glow of the Arduino turning on for just a moment, and I'll do that again in case you didn't catch it the first time. And it turns off almost immediately. So something in this latching circuit isn't working, and I cannot seem to figure it out. So I just want to show you guys the behavior that I'm experiencing, and if you guys have any sort of suggestions on how to fix this, please leave a comment in the comment section down below. I would love to hear your thoughts. But obviously something on the latching side of things isn't allowing that Arduino to stay on long enough and latch on.
So this next slick schematic was provided by Ian M on the EEV blogs forum, so thanks Ian, and I call it slick because it uses only one GPIO pin to run the whole thing. And we got our PChannel MOSFET up here, our NChannel down here, and the principle of operation is similar to some of the other schematics in the sense that when this device is first powered, the gate on the P channel is pulled high, so no current is flowing from source to drain, and everything remains off. As soon as the push button is pushed down, it gives a path here to ground, and that's going to pull this low, and now current can flow from source to drain on our P-channel MOSFET, turning our device on. At this point, the GPIO pin comes into effect. So in our first few lines of code, we need to set this input pin as an input, and we need to activate the pull-up resistor on that input. What that's going to do is that's going to pull up the gate on the N-channel MOSFET and latching this path to ground. So the device remains on and it's latched on. And the little trick here is to have this pull down resistor significantly higher in value than the internal pull-up resistor on the Arduino, which I think is a max 50K. And so this is a 1 meg pull down, and all that's doing is that's giving the gate here on the N channel a reference to ground when the device is off, so it's not floating. But of course, when it is on, we want this thing pulled up high, and so like I said, this has to be significantly higher. Also, when the device is on, this acts as an input pin, so when this push button here is pressed down, you'll see an active low signal going to the input pin. Now, monitoring this push button to turn everything off, let's say we have a situation where we see this button is being held for about 3 seconds. Now we can actually switch this GPIO pin to an output, and we can drive it low. Once the button has been released, we can drive it low, and that'll take the gate on the N channel, and it's going to turn this path off to ground. So it's going to unlatch it, and when that button is released, all that's going to happen is that this gate here is going to get pulled high again, and we're going to kill our power to our microprocessor and force everything off. This schematic is very elegant, I think, in my opinion, and it works great on the breadboard, which you'll see here in a second.
So now we have our third circuit in the bottom left-hand corner, and the Arduino is set up with the single GPIO pin to run the whole thing. Now I'm going to connect the ground lead from my power supply, and as expected, nothing starts up quite yet. I'm going to go ahead and press the momentary push button, and you can see the blue glow of the LED indicating that the Arduino is on and it's latched on. I'm going to press this momentarily, just a quick press, and you can see the green LED light up. Now we're going to press and hold for 1 second, 2 seconds, and you see the 2 flashes on the LED. And we're going to go ahead and press for 3 seconds, 2, 3, and once I let go, the blue LED turns off, indicating that the circuit is off. So this thing is operating as expected, and the behavior is predictable.
So this fourth circuit provided by 0999 on the EEV blogs forum has some interesting properties and advantages. And so right away we can see a P-channel MOSFET up at the top here, and its gate is being driven high through this voltage divider here. Now the advantage to this is that if we have a higher voltage battery, we don't need to find a P-channel MOSFET with a very high maximum gate voltage. And so that makes the component selection a little bit easier. And so just like the other circuits, right away this thing is off in its default state. And you can see that there is an external voltage regulator right here. This could be pretty much just the built-in voltage regulator on the Arduino, so you can pretty much disregard that part. But this circuit is off in the default state. And so when we take our switch here and we turn it on, or we press the switch on, what's going to happen is that's going to provide a path to ground through this N-channel MOSFET down here. So its gate is going to be driven high, and we're going to get a path to ground, and the gate on the P-channel MOSFET is going to be pulled low. And what that's going to do, it's going to allow current to flow from source to drain into our voltage regulator, and we're going to be able to turn our microprocessor on. You'll notice down here that there is an MCU out line, and so that is a pin on our Arduino or microcontroller, which in the first few lines of code, we're going to have to set high, and that is going to drive this second N-channel MOSFET. We're going to drive that gate high, and it's going to latch this device on. So we're going to get our path to ground through here, and it's going to maintain the gate on the P-channel MOSFET low, keeping the current going into our microprocessor. So now the thing is latched on. From there, one thing that we can also notice is that there is an input here on this line, so the MCU in. Now it's being tied to the voltage out of our voltage regulator, and it's done through this diode here, and so it's actually being clamped to this line. So we're only the input pin here is only going to see the voltage after the voltage regulator because it's being clamped to that line here. But whenever this button is pushed, when the whole device is on, it's going to see that input coming from, again, this pin right here. And so you're only going to ever see about 5 volts on the input. You're not going to see the 12 volts coming from the battery, which is great. And now through the software, we can monitor the input again and check to see if we have a hold on the momentary push button. And if we do, then we can drive that MCU line low again, and that's going to basically just turn this circuit back off. It's going to be able to allow the gate on the P channel to be driven high again. It's going to kill the output on our voltage regulator, and everything is going to be forced off. Now, the only other thing that we don't see here that I've done and was suggested by 099 himself on the forum was take this MCU out and actually pull it low. So we can pull this low with a, maybe I think it was a 10K resistor to ground. And that's just so that when this device is off and there's no current and nothing flowing through the P-channel MOSFET, this pin isn't floating. It's going to have a reference to ground, and otherwise this circuit is pretty straightforward and it works great, and you'll see that in the next clip. And so now we have our fourth circuit in the top right hand corner here with the single P-channel MOSFET and the 2 N-channel MOSFETs. And so when I connect the ground lead, you can see here that the circuit predictably remains off, and it's not until I press this momentary push button that of course we have power and it is latched. And now, with a single button press, you can see that the LED lights up once. As we hold it for 1 second, 2 seconds, you can see the 2 flashes of the LED. And as we hold it for 3 seconds, the device powers off. So again, this circuit seems to be very reliable and very predictable. And so I found this 5th and final circuit online from something called an Arduino. And I have no idea what an Arduino is or what it does, but it does have this power latching circuit that's achieved through this P-channel MOSFET and this NPN transistor down here. So similar to the other circuits that we reviewed, when the device is off by default, the gate on the P-channel MOSFET is being pulled high, not allowing any current to flow to our voltage regulator. And we have our momentary push button down here, so when that is pushed, that's going to provide a path to ground. So we're going to come through here, through this diode to ground, pulling the gate low on the PFET up there, and that is going to allow current to flow into our voltage regulator, and our microprocessor is going to turn on. And in the first few lines of code, we're going to take our output, which is here, and we're going to drive the base on the NPN transistor high, and that's going to latch our device on. So now the device is latched on. We can take a look at the input here. So this is a digital input, and this is going to be pulled low. So it's going to be an active low when the momentary push button is pressed when our device is on. So again, path to ground, and there's going to be an active low signal on our input. Now, the only disadvantage I think I see to this circuit here is this 100K resistor that's pulling this line up. It actually is put before the PFET here, and I think that is going to provide a little bit of a current draw when the device is off. So through our processor, it's going to have a path to ground, and there's going to be a slow leak through that line there. So I think one improvement that we can make here is get rid of the 100K pull up before the PFET and put it after. And so by putting it after and then going to our digital input, that's not going to see that leak because this thing's going to be off when the device is off, and this line is going to be dead. So I think that could be a slight improvement to this circuit. And one other thing that I noticed when I was prodding around with the voltmeter was that this input is actually constantly seeing about 5.5 volts rather than 5 volts. And so I'm not really sure why. Maybe one of you guys might be able to explain that to me. But the recommended input on a Arduino is only about 5 volts, so it's about a half volt too high. I don't see any damage being done, at least to my Arduino, but for those of you guys out there who are quite picky about this sort of thing, you might want to try and resolve that issue before using this circuit. Otherwise, it works as expected, which again you'll see in the next clip on the breadboard. So in the bottom right hand corner here we have our fifth and final circuit, and I'm going to go ahead and connect the 12 volt leads. And of course the power remains off, and it's not until we press this momentary push button that we get the latching action of the circuit and the Arduino remains on. With a single push, you can see there's a single light of the LED. Pushing and holding for 2 seconds results in the double flash, and pushing and holding for in excess of 3 seconds results in the device shutdown, just as expected. And as I explained in the schematic, I took the 100K resistor that goes to the input line and I moved it to the 5 volt line off the Arduino, and so that way during this power down phase we don't have any sort of current draw. And I did test it with the multimeter and there is 0 current draw. And so there you have it. This is the fifth and final circuit and we are done.
And so that's it, guys. That's 5 different circuits to help you tackle the soft latching power switch problem. And each one has its advantages and disadvantages. You can obviously choose which one suits your needs the best. Now keep in mind that you also don't have to go with a circuit like this. There are specialty ICs out there to perform the same functionality in a very, very small footprint size. So look up the part number LTC2954, and this is a push button controller IC, and it's meant to perform all these functions in a very small package size. So if you're looking to save board space, look into that component there. Otherwise, I would love to hear in the comment section down below exactly what you guys are working on and how you plan on integrating these circuits into your project. And if you guys found this video very helpful, I would really appreciate it if you left a like on this video and checked out some of my other videos on my channel. And if you really like my content, of course, please subscribe. Thanks guys for watching, and I'll see you in the next video.